a specific cloud infrastructure platform such as OCI, or services like Docker or on-premises infrastructure. Providers in Terraform are essential components that facilitate the interaction between Terraform configurations and specific Terraform platforms or services. Providers are plugins that serve as a bridge between Terraform and the target platform, allowing Terraform to manage resources, configurations, and deployments on that platform. Each provider implements its sets of resources, data sources, and functionalities specific to that platform. There are three types of providers. Cloud providers. These providers interact with cloud platforms like AWS, Google, and Oracle Cloud Infrastructure. They allow Terraform to create and manage virtual machines, networking components, storage resources, and other cloud resources. On-premises providers. Terraform allows support on on-premises infrastructure management through providers like VMware, OpenStack, and Docker. These providers enable the automation of physical and virtual infrastructure within private data centers. Specialized providers. In addition to cloud and on-premises providers, Terraform has specialized providers for managing services such as DNS, databases like MySQL and PostgreSQL, content delivery networks, CDNs, monitoring tools like Prometheus, and more. Understanding providers is key to leveraging Terraform's full potential. By using providers, you can manage a diverse set of infrastructure components from a single configuration file. Now, let's take a look how to configure providers in Terraform. At the top, we have the required providers block. This block specifies a variable name for the provider and sets its value to provider identifier. In this example, we have a variable named OCI for the Oracle Cloud Infrastructure provider. The source is set to Oracle/OCI, indicating provider's official source. The provider identifier serves for two main purposes. Source location. It tells Terraform where to fetch the provider plugin from, whether it's Terraform registry, a private registry, or another source. Version control. Combined with the version attribute, it ensures that Terraform uses the correct version of the provider, which helps maintain compatibility and stability across your configurations. Below that, we have the provider block. This block includes the authentication details and settings needed to connect to the provider. For the OCI provider, we need to specify the tenancy_OCID, user_OCID, fingerprint, and the private key path, along with the region. You can use these values directly or reference values on a terraform.tfvars file, for example. These values are used to authenticate and configure the provider, ensuring Terraform can manage resources in the specified environment. Here is another example of a provider configuration on OCI. The required provider block is the same as the previous example, but on the provider block it's using a different type of authentication, token-based in this case, and different parameters are provided. By specifying the provider identifier correctly, you ensure that Terraform can locate and use the appropriate provider plugin to manage your infrastructure resources. This identifier is essential for linking your configuration to the actual provider code that interacts with your cloud or on-premises services. Thanks for watching and see you in the next lesson. Hello and welcome. In this lesson, we will look into the Terraform resources concept. In Terraform, resources encompass a broad range of infrastructure components essential for building and managing modern IT infrastructures. These resources are the building blocks that Terraform interacts with and provisions based on your configuration. They can be categorized in several types, each serving distinct purposes within your infrastructure. Let's break down the components of a resource block. The resource type identifies the kind of resource you are creating. In our example, OCI core instance specifies that we are creating an Oracle Cloud Infrastructure Compute instance. Several essential resources like compute, network, storage are grouped under the core group. This is important to remember when navigating the resources documentation. The resource name is a unique identifier within the configuration for that resource. Here it's named example_instance. Inside the resource block, you define the configurations and attributes for the resource. These configurations specify the settings and properties for the resource. Attributes are key-valued pairs that define the properties of the resource. There are required and optional attributes according to the resource's type. Here we see the attributes and their respective values. In addition to standard attributes, you can also include metadata for additional configuration. For example, the metadata block can include SSH keys for the instance access. To learn more about different resources and their attributes, you can visit the Terraform registry. By defining resources in Terraform, you can manage and automate your infrastructure efficiently. Each resource block is a declarative way to specify the desired state of your infrastructure components. Thanks for watching and see you in the next lesson. Hello and welcome. In this lesson, we will look at the Terraform output concept. In Terraform, outputs provide a mechanism for extracting and displaying information from deployed resources after applying Terraform configurations. Outputs are defined within Terraform configuration files to specify which attributes or values of resources should be exposed and made available for reference or use outside of Terraform. Let's look at a simple output configuration. On the left side, we have a resource block defining a subnet resource named example_subnet. On the right side, we have a resource block defining an OCI instance named example_instance. Here we use an output from the example_subnet resource for the subnet_id attribute, referencing it as OCI_core_subnet.example_subnet.id. By using outputs, we can dynamically link resources together. In this example, the instance resource references the subnet resource, allowing Terraform to manage dependencies and ensure resources are created in the correct order. Back on the left side, we have an output block that also references example_subnet. Used this way, this output will display the subnet ID after a configuration is applied and the resource is created, for summarizing purposes. This concludes our lesson on outputs. Thanks for watching and see you in the next lesson. Hello and welcome. In this lesson, we will cover Terraform modules. Modules in Terraform are self-contained packages of Terraform configuration that are managed as a group. They enable you to encapsulate and reuse infrastructure components, making your configurations more modular and maintainable. Let's look at an example to understand how modules work. On the left side of the slide, we have a module file located on modules/compute-instance/main.tf. The modules directory is placed on the same directory as the root configuration file. First, we will define several variables such as instance_name, image_id, and subnet_id. These variables allow the module to accept inputs, making it flexible for different use cases. The resource block within the module defines the OCI instance named example_instance. it uses the variable from the configuration. On the right side of the slide, we have a main configuration file that uses the module we just defined. The module block in the main.tf file references the module located at modules-compute-instance. We provide values for the variables defined in the module, and those values will be used on the instance creation. Using modules, you can create a standardized set of configurations that can be reused across different parts of your infrastructure. This approach simplifies management and promotes consistency, as changes made within a module can be propagated to all instances where the module is used. By encapsulating your infrastructure components into modules, you can create more maintainable and scalable configurations. Thanks for watching, and see you in the next lesson. Hello and welcome. In this lesson, we will look at the Terraform state file. Terraform state is a critical part of how Terraform operates. It keeps track of the infrastructure resources that Terraform manages. The state file, typically named terraform.tfstate, is used to map your configuration to real-world resources. On the right side of the slide, we see an example snippet of a Terraform state file. This JSON file includes various details such as version information, Terraform version, managed resources, and their attributes. Let's break down the key components and concepts related to the Terraform state file. Terraform states tracks the current state of your infrastructure. This includes information about the resources you've created, their configurations, and their dependencies. State files helps Terraform understand the dependencies between resources. This ensures resources are created, updated, or destroyed in the correct order. The state file contains detailed attributes of each resource. This includes configuration parameters, metadata, and any changes that have occurred since the resource was created. Terraform uses a state locking mechanism to prevent multiple operations from being performed on the same state file simultaneously. This is crucial for ensuring consistency and preventing conflicts when multiple users or systems are making changes to the infrastructure. The state file can contain sensitive data such as resource attributes and configuration details. It's important to handle the state file securely to protect this information from unauthorized access. Terraform supports storing state files remotely using backends such as OCI Object Storage Buckets, OCI Resource Manager, or HashiCorp Cloud. Remote state storage provides better security, collaboration, and disaster recovery capabilities. Understanding and managing Terraform state is essential for ensuring your infrastructure is correctly maintained and updated. By leveraging state tracking, dependency management, and secure storage policies, you can effectively manage your infrastructure as code. This is the last lesson of these modules, and a lot of concepts were introduced. Don't worry, in the next modules and lessons, when we start to practice writing and deploying configuration, the puzzle will start to take shape. Thanks for watching, and see you in the next lesson. Hello and welcome. In this module, we will create your first Terraform configuration with OCI. In this lesson, before jumping on the Terraform configuration, we will show the basic setup required. This process typically includes downloading the appropriate Terraform package for your operating system, extracting the files, and adding the Terraform binary to your system's path environment variable for easy access from the command line. Once installed, you can verify the installation by entering Terraform version in your terminal or command prompt, which should display the installed Terraform version. Alternatively, if you are working with a cloud environment like Oracle Cloud Infrastructure, you can leverage Cloud Shell, a browse-based shell environment that comes with pre-configured with Terraform. Cloud Shell provides an easy, ready-to-use environment with Terraform configured and integrated with your OCI tenancy. In this course, the demos will use Cloud Shell to simplify for those that want to reproduce the steps on their environments. Before start writing the configuration, understanding the parameters evaluation order is crucial for proper configuration. Terraform checks parameter values in the following order. The Terraform configuration. It has the highest priority, directly specified in the provider block. Environment variables. Check it if it's not set in the configuration. For example, set OCI underscore tenants underscore OCID as an environment variable. Non-default profile in the OCI config file. Use it if not found in the environment variables. For example, you can have a profile called dev inside your OCI config file just for development. And finally, the default profile in the OCI config file as a failsafe. By following this evaluation order, you ensure accurate and efficient Terraform configurations for OCI. If you write the parameters inside the configuration file, the provider section will look like this. In the example, I mixed values and variables. No special reason, just because we can do that. Using Linux environment variables, this is how it will look like. You can either export the required authentication values as environment variables, or source them in different bash profiles when executing Terraform commands. If you primarily work in a single compartment, consider exporting the compartment OCID as an environment variable. The tenant's OCID is also the OCID of the root compartment, and it can be used where any compartment OCID is required. On Windows, this is how you can export the environment variables. When security token is used, your provider block can be as simple as this. Authenticating using security token is secure and effortless. The token expires after some time as a security measure. Even if you don't terminate the session, the expiration will get you covered. This concludes this lesson, and next we will write our first Terraform configuration. Thanks for watching, and see you in the next lesson. Hello and welcome. In this lesson, we will create our first Terraform configuration and navigate through the Terraform workflow. The Terraform workflow consists of the Terraform configuration file. In this step, you will define the infrastructure you want to deploy using a configuration file written in HashiCorp configuration language, HCL. This file specifies resources, variables, and providers. Step 2. Terraform init. Once your configuration file is ready, the next step is to initialize your Terraform environment using the Terraform init command. This command sets up your working directory, downloads necessary provider plugins, and prepares your configuration for deployment. Step 3. Terraform plan. With your environment initialized, you can use the Terraform plan command to create an execution plan. This command compares your configuration with the current state of your infrastructure and shows you what changes will be made without actually applying them. Step 4. After reviewing the execution plan, you can apply the changes using the Terraform apply command. This command will create, update, or delete resources as specified in your configuration, bringing your infrastructure to the desired state. Step 5. Terraform destroy. When you need to tear down your infrastructure, you can use the Terraform destroy command. This command destroys all the resources defined in your configuration, ensuring a clean environment. By following these 5 steps, you'll be able to efficiently manage and automate your infrastructure deployment with Terraform. In Terraform, all the configuration blocks can be placed in files with the tf extension. The first one is often named main.tf. This file contains the necessary configuration for your infrastructure, including provider settings, resource definitions, and other configurations. Later, we will show how multiple files can be used. For now, we will use a single file to allow to focus on another aspects. At this point, I will change to the OCI console and start my code editor. I already have a pre-created compartment called IAC that will be the target where I will create my resources. Starting the code editor, you just have to come to the developer tools, click on code editor. If it's the first time that you are accessing it, it's going to take some time to load, but after that is how it will look like. From here, I will create a directory. You can see the list of the files that are present in your home directory within Cloud Shell. And there I will create my IAC directory. In this IAC directory, I will have my first file called main.tf, and I will start to populate this file with my configuration. I have first my provider block with the required configuration. You can notice here that there are 4 lines that are commented out. These lines are commented out because we are using Cloud Shell. If you are not using Cloud Shell and you decide to do that on your local machine, you will have to uncomment this line and populate accordingly. If you decide to use the token authentication, it can be simpler than that. Now that we have the provider, let's add a block with the simplest resource that we could create within OCI, a VCN. So we will have the resource block, we will have the type of the resource, OCI_core_virtual_network, and the unique name within the configuration. Here you will have the compartment name. I will have to replace with the my compartment. And I already filled some of the parameters that are necessary to create the VCN, the CIDR block, the DNS label, and the display name. To get the compartment name, I will use a new tab and I will navigate Identity and Security, Compartments. Here's my IAC compartment. I'll copy the value and place that value in my configuration file. And with that, step 1 is done. We have our configuration file. I can come here, File, Save, and step 1 is ready. Now it's time to initialize my working environment. To do that, I will start a terminal, so I don't have to open a new window. And I will have access to Cloud Shell here. Currently, I'm not on the same directory, so I will change for my IAC directory. You can see here my main file. And let's start with Terraform init. It will download the required plugins, any required configuration that might be necessary to download as well. It will do that, and Terraform has successfully been initialized. If we take a look at the directory now, we will see the log file and we will see a .terraform directory. Inspecting this directory, we can see that the provider for OCI was downloaded. We can see the version, we can see all the files that are part of it. With that, we finished our second step with Terraform init. After running Terraform init, it's time to run Terraform plan. Terraform plan will load the configuration and show an action plan of what's going to be created, what's going to be deleted. You can see that here on the screen, and at the bottom we have a summary showing that we will create one resource, our VCN. There's nothing to be changed and nothing to be destroyed. You have the option to save that plan to a file, and when you run the apply, you can run the plan that you reviewed. But we're not going to save this. We're going to just run apply and ignore the alert that it might not be the same plan. We have control of the environment, so it's not going to be a problem. Let's clear the screen again. Terraform apply. We will see the same summary that we saw before, but now we have to enter yes as the action that we actually want to perform those actions, and voila, the resource was created. You can see that OCID was printed here, and if we check on our other tab, we can go to the virtual cloud networks, and we have VCN1. If we check here the OCID, it ends on YRXA. We can check here YRXA, the same VCN. Now, if we don't need that resource anymore, it will be time to destroy and finish the workflow that we have for Terraform. Let's clear again the screen, and now Terraform destroy. With Terraform destroy, it will read the state file and will create a plan of what needs to be destroyed, and adjusting the order and making sure that the environment is clean of what was created before with the configuration. Setting yes here, we will confirm our intent, and after running, it's good as gone. If we come back here to the other tab, Virtual Cloud Networks, that network is gone. With that, we conclude our first Terraform configuration. In the next lesson, we're going to check how we can create the same configuration using multiple files to making it easier to organize your environment. Thanks for watching, and see you in the next lesson. In this lesson, we will explore how to modify Terraform configurations to add more resources, improve reusability, and enhance your infrastructure management capabilities. We will use variables and split the main.tf file into smaller files. We will also create a Terraform.tf vars file to accommodate information relevant to this environment. If another environment is necessary, a similar file can be created with the correspondent values, reusing the other files without any change. Let's get started. Splitting the files makes it easier to organize the resources and increases the readability. This is how our configuration will look like after we split. You can split the files as you wish. Terraform combines them and sort the order properly before applying. Picking up the file from where I left, let's start by creating a variables.tf file. And on this file, I have already set the variables that we're going to use on my notes here. So I will just paste the values. Once that file is saved, when I start to replace here, the autocomplete will help me. So var.region for this part here. For my compartment, I will have var.compartment.ocid. Similarly for the other variables, so var.vcn01 cider block, I'm going to use the display name as the DNS label for this guy, so same name here and same variable again on VCN01 display name. Now that we replaced the variables, let's move the contents of the provider section to a different file. I will copy this information here. I will create a new file called provider.tf. It's on the correct path. I'm going to paste the contents here. Oh, I copied more than what I should. Let me remove here. Let me go back, place this where it belongs. And okay, now that we split the files, we have to create a file that will hold the values for those variables as they are not present in the code anymore. Now it's time for Terraform tf-vars. For my environment, I already have here on my notes a copy. So I will just paste the values here. And let's give it a try and see if it works. I will go to the terminal again. Terraform validate to make sure that I don't have any syntax mistakes. All good. Let's clear the console again. Terraform plan. And let's see what we have. Yep, our changes are okay. It will create one VCN as we created before. I will save the time and not do the apply because we're going to do a couple more changes. Let's go back to the slides and to see what are those changes. Now, let's explore how can we incorporate Terraform modules to enhance our infrastructure management and promote reusability in our configurations. To incorporate modules into our Terraform project, I will first identify the modules that align with the new resources or functionalities we want to add. These modules can be sourced from the Terraform registry, community-contributed repositories, or custom-built modules within your organization. In our environment here, we will create them from scratch. Our module will live in the vcn_module directory. The first two files I will mention are the main.tf that will hold the resource configuration and the variables.tf that will contain the variables. Remember that Terraform defines scopes and those variables are only used within the module. The last file is the outputs file. Because of the scopes defined by Terraform, any information contained in a module can only be reused outside if you define an output for it. Here's the output file that we will use. Once the module is finished, it's time to configure the main.tf file to invoke the module and to create the resource. Now let's do it for real. Back in the console, let me close these files here. We don't need the provider. The resource that we have, it's a VCN, so we will create a module for the VCN. As per we defined it before, we will create our vcn_module directory, and within that directory we will have our module files. So vcn.module, let's create main.tf. No, it got the wrong path. And we close here. VCN module. Main.tf. We'll go here. Now that we have the directory, let's create our module files. Let's click on it, make sure that it's selected. Yes, it's on the right directory. Main.tf. Okay. The contents of main.tf for the module. It's where we're going to define the resource. So we'll paste here. These variables we are going to define next on the variable.tf. Before doing that, let's save, make sure that it's okay. It's marking as red here because we have several variables that were not declared yet. So no declaration found for the variable. As soon as we create the file, that should be fixed. So variables.tf, inside variables.tf, I already have on the nodes here, so let's paste the values. Let's save the file. We can close this file now. As you can see, the error is gone. And let's create the last file, the outputs.tf. I also have that on the nodes here. Remembering that if you want to use it outside, you have to declare those values here. File, save. And with that, our module is created. We have here our 3 files inside the VCN_module directory. Now what we have to do is to replace this resource block here with the invocation of the module. I will not delete it for now, so you guys can compare how it looks like. I will copy from the notes. I will paste it here. So instead of calling resource, I'm going to call the module, the name of the invocation, where that source module is. It's on the same directory of the main.file, so /, and the name of the directory. I have these variables here that were declared for the main.tf on the root of the directory. Those values here, as you remember, it's on the terraform.tfr file. And once they get the values from there, they will replace the variables here that will, in their turn, replace the variables inside the module. I don't need that section here anymore. We can get rid of it. Let's save the file. And let's go back to the terminal. Clear the terminal. First thing that we have to do after introducing a module is to run Terraform init again so it can validate the module. Terraform init. And that's it. Initialized successfully. Now let's clear. And let's try to run a Terraform plan and see what's going to create for us. Terraform plan executed, and we see the plan here, similar to with the previous output that we have, but now this time is coming from the module. Let's go ahead and do a Terraform apply. Let's say yes as the intended action. Once it finishes running, let's take a peek on another tab and see that we have our virtual cloud network created. Going back here to the other tab, let's do another thing. I will copy this module and I will create another VCN. But this time I will not create variables, I will just use the values directly here. So I will replace the variable with the value here of the cider block. I'm going with a different cider block, /16. Our display name, DNS label, I will use VCN02. The compartment it will be on the same compartment, so I can reuse the variable. And for the display name, I will also use VCN02. Let's save the file. While the file is saved, let's clear the console and run Terraform plan again. I have a mistake here. Oh, as I invoked the module again, it's time to run Terraform init once more. It validates the module, and if I run a Terraform apply, it will create my second VCN. Terraform apply, yes. It executed, one resource added. If I go back here, VCN02 as intended. So with this, we finish our module implementation on Terraform, and also the demonstration on how to use variables, use different files to organize your code and improve readability and reusability. This concludes our module on Terraform. We just scratched the surface of what Terraform can do for you, but these basics will allow you to explore our next module, OCI Resource Manager. Thanks for watching, and see you in the next lesson. Hello and welcome. In this section, we will cover OCI Resource Manager, a managed service that automates the deployment and management of cloud resources using Terraform. In this lesson, we will introduce you to the concepts and functionalities of OCI Resource Manager, helping you understand its role in cloud infrastructure management. Let's explore the key concepts of OCI Resource Manager. These include configuration source provider, configuration, stacks, action, jobs, and templates. Understanding these concepts will provide you with a solid foundation to effectively use OCI Resource Manager. We begin with configuration source providers. Configuration source providers allow you to streamline access to external configuration data, facilitating efficient management and integrating of settings across your cloud infrastructure. OCI Resource Manager supports several configuration source providers, including Bitbucket, Bitbucket Cloud, GitHub, and GitLab. These providers help you integrate your source control systems with OCI, ensuring that your infrastructure configurations are consistent and easily manageable. Next, let's talk about configuration. In OCI Resource Manager, configuration involves defining variables, resources, and providers in your Terraform files. This process sets the foundation for managing your cloud infrastructure. In the Resource Manager realm, every time you hear about configurations, it's referring to your set of Terraform files. Next, we have stacks. In OCI Resource Manager, a stack represents a collection of Terraform configurations that define your infrastructure resources. Stacks allow you to manage and deploy related resources as a single unity, ensuring consistency and efficiency. Stacks are subject to actions, enabling you to manage and modify your infrastructure. Here are the key actions available in OCI Resource Manager. Plan. This action shows the changes required by the current configuration, helping you understand what will be created, updated, or destroyed before making an actual change. Apply. This action creates or updates your infrastructure based on the configuration you've defined. Destroy. This action destroys previously created infrastructure, allowing you to clean up resources that are no longer needed. Edit. This action allows you to change the configuration, providing flexibility to adapt to new requirements or adjustments. Drift detection. This action detects differences between the current configuration and the actual infrastructure, ensuring consistency and helping identify unexpected changes. Import state. This action imports the current states to reflect existing infrastructure, allowing you to manage and track resources that were created outside Terraform. Next, there are jobs. Jobs represent operations performed on stacks, such as creating, updating, or deleting resources. Understanding the job's lifecycle is crucial for managing these operations effectively. Here are the lifecycle stages of jobs. Accepted. The job request is received and accepted. In progress. The job is currently being executed. At the end of the journey, if the job completed successfully, it succeeded. If the job did not complete successfully, it failed. If the job is in the process of being cancelled, it will be cancelling as operations are being terminated, to finally change to cancel. Each job progresses through these stages, allowing you to track its status and manage your infrastructure operations efficiently. Next, let's talk about templates. In OCI Resource Manager, templates provide standardized configurations that simplify and automate the deployment and management of your cloud resources. Templates allow you to define common infrastructure patterns and reuse them across different environments. This enables you to ensure consistency and efficiency in your deployments. By using templates, you can easily manage complex configurations and streamline your infrastructure management process. Let's put all together. We start with a configuration that can come from different sources, creating a stack. Using the plan action, it will pass through the different lifecycle stages. Once it succeeds, it will be ready to apply, that will go through its stages, to finally provision the resources. Now that the introductions were made, I wait for you in the next lesson to put all these concepts together and create your first stack. Thanks for watching and see you soon! Hello and welcome. After introducing Oracle Resource Manager concepts, now it's time to see how it works from a hands-on perspective. Before we get started, let's look at an overview of what we will be doing. First, we will compress our existing Terraform configuration into a zip file. This is essential for uploading your configuration to OCI Resource Manager. Next, we will initiate a new stack creation wizard in OCI. Select the zip file as your configuration source. This process helps OCI Resource Manager understand the structure and contents of your configuration. After uploading the zip file, we will input the necessary variable values. These variables help customize your stack for different environments or use cases. Once input, your stack configuration is ready. Proceed with the plan action. This step shows the changes required by the current configuration. Review the execution plan plan to understand what will be created, modified, or destroyed. Finally, execute the apply action to create or update your infrastructure. This step will apply the changes outlined in the plan, bringing your resources into the desired state. Now that we finished the overview, let's see how it looks in the console. I will start from the point where I stopped at after the Terraform module, because we built a configuration there. I'm already on that directory, and I have here my configuration files. So, first step is let's create a zip file, download that file, and from there we will create our stack. To create a zip file, I will use the command line just for simplicity. So zip minus UR. I will create on the directory below so it doesn't get mixed up with everything that I have. I need all my TF files. I don't need the Terraform state, or if you have on the directory TF vars file, so only star.tf. As I have the modules there, my module is called VCN module. I'll have the name of the directory here. As I used the R option, it will be recursive. I don't have to specify the files inside the module. So I have my files here added to the zip file. If you want to confirm that they are there, you can use the unzip -L command and you point to the zip file, and you will have the list of the files that were included at the zip file. Now I have to download. Easiest way to download is if you come here on the left side on the list of files, you will see myconf.zip. You can right click, download. You should see the download dialog on your browser. I will open my file explorer here and minimizing Cloud Shell, I can go to the navigation menu, Developer Services, Resource Manager, Stacks. I will start the wizard by clicking on Create Stack. I already have selected my configuration. I will say that I want a zip file. I will browse the file. It's already on my download directory here. I will choose to open. The file is listed here. I could have used an object storage bucket or a folder, but using the zip file is just simpler from where we are. You can give a name to that. My first stack. You can add a description, the compartment where it will create that stack. Terraform version, we can go with the latest. The latest supported with Resource Manager is 1.2. And when we click on Next, as we have some variables in our configuration, it's prompting us to fill those variables. The first two, it checked from the input that you had before with the compartment, and we are using the Ashburn region, so it's already filled for you. We will enter the value for our subnet CIDR block, and this is VCN01. And by clicking on Next, we will review and we'll create. There's a button here, Run Apply. If you check this box, it will automatically create the stack and run the apply command for you. As we want to go through all the steps, I will leave this unchecked for now and click just on Create. And that's it. Our first stack is created. Now we can run the same actions that we have on Terraform and a couple more actions. We can use plan, apply, destroy. We can import the state. There's a whole bunch of options that we can go from there. Let's start with the plan and see how it looks like. It will give a plan like if you were using the output option when you run a Terraform plan -out. And after running plan, it will start to process it. I'll get back in a second after the plan is finished. During the execution of the plan, the logs will be updated with partial logs. You can check that. Once it turns green, you can scroll down the page and you can review the whole output of the plan command. As you can see here, our first VCN where we input the variables. We have our second VCN that the values are inside the configuration file. And you can see the summary of the plan, adding 2 resources, nothing to change, nothing to destroy. Once the plan is finished, we can move back to the stack details, and we can run and apply. The apply can be based on the plan that we just executed, or it will do with automatically approve, running whatever is on the configuration. If you run based on the plan that you have here, you are sure that it's the plan that you reviewed, no changes has made in between, and you have more assurance and more control over the whole process. I will click on apply, and the same way as the plan command, the logs will be displayed here during the execution, and the full logs will be displayed when it turns green. Now that the job finished and it was succeeded, it is green as on the plan. You can scroll down, review the logs, and we have the result here, apply complete. If you go back to the stack details, you have a summary of the jobs that we've executed so far, the state of those jobs, and that concludes the creation of our first stack, running in apply and finishing to deploy the configuration. I can review the created resources going to the virtual cloud networks. Here we can see the 2 VCNs that are declared in our configuration. After verifying that the resources were created properly, now I will show you how to edit a stack. Let's go back to the stacks. Within the stacks details, you will have the edit button, where you will have 2 options. First one, when you click on edit stack, you have the option to point to a folder in a zip file, and you can upload a new version of your configuration. If we edit our files that we have on Cloud Shell, we would have to create a new zip file and upload it here. If we don't change anything on the configuration, we still have the option to go on next and change the value of the variables that we have. In this case, I would change from VCN1 to VCN2. Something important to remember is that some of the changes that you make on the variables or attributes of a resource might request that resource to be recreated, so it will be destroyed and created again. And that's the case for the attributes like the CIDR block or the name of the VCN. After saving the changes, I will run a plan. In that plan, we will use the new variable values that I set. After the plan finishes and succeeds, when you review here, you can see at the summary that 1 object is going to be destroyed and 1 is going to be added. Nothing happened so far because we just planned. So let's go ahead and apply. And I'll be back when it finishes. Now that the apply finished and it was successful, let's go back and check our resources. And where I used to have VCN01, now I have VCN02. The second way to edit a resource. Now let's check the second way of editing a stack. I will go again to the stack details, and I will select Edit Terraform Configuration in Code Editor. If I click here, it will open Code Editor. As I have Code Editor open, I will show you another way that you can navigate and find your stack. So you can click on the plugins. It's going to be the third icon. And within there, you find Resource Manager. You can start navigating on the compartments. And as you navigate, you can find your stack. In this case, I have here my first stack. I have my main item here. I have my variables file. In this case, I will come here and I will change the VCN, my VCN to VCN3. I'll change here to VCN03 as well. And after you finish changing the configuration, you can right-click on your stack, save changes, and you also have the options to run a plan action directly from here or even in apply. I will run directly in apply as we've been running the plan and apply. I will go directly with the apply now. Once I click here, if I minimize, I can refresh this page. Oh, no, because it's open. But if I click on stacks, click over here, I have an apply job being processed here. Let's wait until it finishes, and then we're going to check if the change was applied to the resource. The apply action finished, it was succeeded. If we go again to our virtual cloud networks, where we had my VCN, now we have VCN03. With that, we finish our demo on how to create your first stack and how to modify an existing stack. Thanks for watching, and see you in the next video. Hello and welcome. In this module, we will explore how Terraform source providers can be used as the repositories for your configurations. Configuration source providers give you streamlined access to external configuration data, facilitating efficient management and integration of settings across your cloud infrastructure. OCI supports Bitbucket Server, Bitbucket Cloud, GitHub, and GitLab as configuration source providers. To use a configuration source provider, we will follow these steps. First, create a repository that contains our configuration. Next, create the service provider on OCI. Then, start the new stack wizard and select the service provider as the configuration source. Input variable values if present, and the stack will be ready. After the stack is ready, as usual, the plan action and the apply action. Now, let's jump on the console and see how it works. In between videos, I deleted all the stacks and resources. So we're starting with just the files that we have on Cloud Shell. At my Cloud Shell, I will make sure that I have my key SSH key pair. Those will be used to authenticate against GitHub if I have to write files over there when I'm changing the configuration. Next step is go to GitHub, and I will make sure that I have that SSH key working with my account. So I click on my profile, settings, SSH keys. I will add a new SSH key, IAC demo. I will paste the content of the public key file. So I can do a cat ID RSA pub, posting this contents there. That will finish the configuration of the key on GitHub. Once the key is successfully added, let's test and make sure that it's working with GitHub. To do that, SSH dash capital T git at github.com. As I'm using the default name for the key, I don't have to specify it over here. When I hit enter, it's the first time I'm trying to connect to GitHub. I have to accept the key fingerprint of the server. Yes, I can see my username here. You successfully authenticated. GitHub does not provide shell access. That's the expected answer that we are looking for. Now that the key is ready, let's go back to GitHub and I will create my first repository. I click on the new button. I'm going to call it IAC demo. IAC course stack. We don't have to change any of the values, and we can go and create repository. Oh, I didn't select the owner because I have multiple profiles. I select it here. It's available. So I can finally go and create my repository. So now I can go to Cloud Shell and initialize the directory that I have there. I will copy these instructions here and go into Cloud Shell. I have to change to my directory there, IAC, clear. I will paste all the instructions. I will hit enter here. My directory is configured. As soon as I can set up the directory as and initialize it as my repository, the GitHub icon will show here with files that should be added. We have all the files, but we won't be using all the files. We have to create first a git ignore to avoid putting files like Terraform state, the tfvars, and so on. So let's create a .gitignore file. I will click on the directory. I'll click to add a file. .gitignore. I have from my notes here the content of the file. Closing this will save the file. As you can see here, it moved from 16 to 7 files. At this point, our files are not there yet. So what we need to do is we can come over here. We can click on changes. It will select all the files and it will be our first configuration. We will commit. Once it's committed, we can push. And by pushing, it will be sent to GitHub. So if we change tabs here and we refresh this page, we have our configuration set on GitHub. We have read-write access. We can move to our next step. Now our directory is configured to use GitHub, but it's not ready yet to use with OCI as a configuration source. Before we do that, we have to set up an access token. In order to create the token, you have to click on your profile, select Settings. On the bottom left, you will find Developer Settings, Personal Access Tokens, Tokens Classic, and by clicking on the button, you will select Generate New Token Classic. For to work with Resource Manager, they have the following permissions: repo status, repo deployment, public repo. You can put a note saying IAC course. You can set the expiration of the token. Towards the bottom, you will find generate token. I will copy the token, and that will be used during the creation. I'll leave it open for now. So coming here, developer services, configuration source providers, configuration source, IAC, GitHub, IAC, GitHub, the compartment where that source will be placed, It's a public endpoint because we are using github.com. If you were using a private endpoint, you could select here. We will change it to GitHub. I'll paste my access token here so I don't lose it. As I'm using GitHub with a free account, my URL will be github.com. github.com. Filling all this information, I can go ahead and click on Create. I don't want to save that with my password manager. If I click here, I will see the details, and I can click on Validate Connection to make sure that it works. Connection validated. Now I'm ready to create a stack using this source provider. To create that, I will go back on Resource Manager, Stacks, clicking on Create Stack. I will select Source Code Control System. I use it GitHub, so I will select GitHub here. When I click on the selection box, I will find the source provider that we just created. I have to pick up a repository. I have one called AIC Demo. It has only one branch. If it had multiple branches, I could select which branch I would want to use. I'm not going to use any custom providers. Stack from GitHub is the name that I will use. We can put the highest version that we have. After selecting the version, I will click on Next. This configuration, if you remember, we have some variables that we're going to fill the values here. VCN01 and the cider block. I will click on Next. And reviewing the values, I can go and create. My configuration is provided through this stack. This stack is created. I messed with the name here, but let's leave as that. And let's run a plan. Once it returns, I'll be back. Now that the plan finished, I will go back here. I will click on Apply to create the resources based on the plan. Once it finishes, I will get back again. Our apply action finished successfully. It created our two VCNs. If we go to the navigation menu, Virtual Cloud Networks, we can see my VCN and VCN1 again. If we want to change the configuration, we can go to the code editor and change the configuration in our Cloud Shell directory. So I will come here, I will change this to VCN02. I'll change the name to VCN02. And now what we have to do is, well, I'll close this to make sure that the file was saved. Once the file is saved, the source control will inform us that there are changes. We can add that change to stage. We can save our commit message, change VCN name. I will commit that change. I will push that change to GitHub, and I can go back on my stack, developer services, stack. And if I run a plan here again, or if I run an apply, it should pick up the change that we just committed to GitHub. I will run the apply just for directly, so you can see that it can automatically approve. We don't have to run the plan. We made a simple change. When it finishes running, we will be back to check what happened. Well, the apply finished. We can take a look here, and we can see that the change that happened, changing from my VCN to VCN2, and that create a replacement. So we have one resource that was destroyed, it was added, and all that was done by changing the file and committing the change to GitHub. If we come here to check our resources, now I have VCN1 and VCN2 that previously was my VCN. With that, we conclude our demo on how to use source control as a source provider for resource manager, and how you will manipulate the configuration, change the configuration, so it can be updated when you need to make changes. Thanks for watching, and see you in the next video. Hello and welcome. In this module, we will explore how Terraform can import existing infrastructure and generate a configuration for it. This is what happens when you create a stack on OCI Resource Manager based on an existing compartment. You will choose the compartment that has the resources that will be imported. You will start the new stack wizard and choose existing compartment and the type of resources that will be imported. Resource Manager will scan the compartment. Then Resource Manager will create the configuration. And finally, the configuration will be added to the stack. Let's jump into the console and see how it happens. First, I will delete the stack that we used on the previous video. This is the stack that we used in the last video. Let's delete it. And we have this warning. When you delete a stack before running a destroy, the resources that were created by that stack, they are left behind. So that's what this warning is about. As I want to create a new stack, and I want to get rid of this one, I will just go ahead and delete. The stack was deleted, but if we come over here, we can see that the VCNs are still there. Let's start to create our stack based on the existing compartment then. I will go again to Stacks, Create Stack. I will go to Create Stack, select Existing Compartment, pick the compartment that I want, IAC, the region where it will the resource discovery will be performed. I don't want all the resources. On this tenancy, there are several other resources that were created, and I just want the VCNs. So I will go with selected, and then I will select the core category, because that's where the network VCNs are. I don't need the custom provider. I will name it from compartment IAC. I will clean up the rest of the name. And I'll be ready to go with next. At the moment, we don't have any variables that will be filled. We can just click on next, just review the values, and click on create. Resource Manager will take a couple minutes to finish this. When it finishes, we will come back and review. After some minutes, the discovery process has finished and the configuration was created into the stack. Let's review what was discovered. I have the code editor open already. I will click on the plugins. Within plugins, I will start exploring the IAC compartment, my stacks, and I have a stack called from IAC compartment. We will have vars.tf with variables, a very simple set of variables as you can see. We will have the provider information, and we will have core.tf with all the components from the core category. I will close the terminal here to make room for more stuff. If you take a closer look, you will see that more resources than the 2 VCNs that we created are present. This happens because when you create a VCN, several other resources are created automatically, and those resources were not part of the original stack. When we do the resource discovery, those resources will become part of the configuration that is being created by Resource Manager. With that, we conclude our demo on how to import existing infrastructure into a stack using Resource Manager. Thanks for watching and see you in the next video. Hello and welcome. In this module, we will explore drift detection. Imagine you deployed a set of resources using Resource Manager, defining everything in your Terraform configuration file. However, over time, manual changes or configurations are made outside of Terraform. The difference created between the configuration in the existing infrastructure is the drift. By understanding and managing drift effectively, you can ensure that your infrastructure remains consistent, compliant, and aligned with your defined configurations. Later, check how to detect and resolve drift on Resource Manager. The process of using the drift detection feature has the following steps. First, you run drift detection. Terraform will analyze your current infrastructure state and compare it to the state defined in your configuration files. A report will be created if any drift is detected. After that, you will carefully inspect the report generated by Terraform. This report will highlight any differences between your actual infrastructure and the expected state defined in your configuration files. Based on the differences found on the report, edit your configuration to incorporate any necessary changes. This step ensures that your configuration files reflect the current state of your infrastructure. After updating your configuration, run the Terraform plan action. This action will show you the proposed changes that Terraform will make to align your infrastructure with your configuration. With the plan reviewed and confirmed, execute the Terraform apply action. This step will apply the changes to your infrastructure, ensuring it matches the state defined in your configuration files. Finally, run the drift detection again once more to confirm that no drift remains. This ensures that your infrastructure is fully synchronized with Terraform configuration. Finally, run the drift detection action once more to confirm that no drift remains. This ensures that your infrastructure is fully synchronized with your Terraform configuration. Let's go to the console and see how it works. In my environment, I already have 2 VCNs that we created on the previous example. Those VCNs are part of a stack, and we will manually change those resources to create the drift. I will go to VCN 1, I have the secured list, and on the secured list, I will add an ingress rule. I will pretend I have a web server running on this subnet that it's exposed to the internet, so port 80, my web servers, and add the ingress rule. Now, if I move to the stack and run a drift report, it will compare what I have on my configuration files and what actually exists on the environment. It will take a couple minutes to run, and I'll be back when it's finished. The drift detection finished, and as expected, we have drift detected. So let's take a look at the report. And when we see the list of resources, they will have the drift status, and we can see that the default secret list is what is modified. If we expand here, we can see what is expected and how is it different. If we look at the bottom of the report, we will see ports 80, and that is the difference that we have. So to fix this now, we have to go to the configuration and add that port as part of the security list. Let's do that. I will close the report. I will go to the code editor. I will select the plugin. As I navigated before, the stack is already open. If not, you would have to go on the compartments, navigate to the stacks on that compartment, and then you find. Then I will open the core.tf and I will try to find the default security list. I can go here, go back on the report. I can copy the resource type. I can go back on the report. Let's try to find, and here is the default security list for VCN2. We're looking for the one for VCN1. Here we have all the rules, so let's go ahead and create a block with the ingress rule for port 80. So I'll copy this block here where we have the rules for the SSH and insert a new block. On this new block, I will change the port to 80. And I will add the description by uncommenting the parameter and putting the value my web servers. Once I do that, I can close the file. I will save my changes and I will run a plan action. Going back to the stack, I will wait until the plan concludes. Let's force a refresh. Plan was accepted, and when it's finished, we're gonna take a look at the details of the plan. We are back, and now that the plan finished, let's take a look. Looking here at the logs, we can see that the default security list for VCN1 is going to be changed, and it's adding an ingress rule for port 80 as we defined it there. So 1 to change, 0 to destroy, nothing to add. The plan was saved. Now it's time to apply this plan. Apply from compartment, IAC, that's the plan that we created. Let's go with apply. And once apply finishes, we're gonna run the drift report again. Now the apply action finished, we can go back to the stack details and run another drift detection. When you're running the drift detection, you can run against all the resources or selected resources. As we don't have that many resources, we can run with all resources without any impact. We will leave the drift detection running again, and we'll be back when it finishes. The drift detection finished, and as expected, it's in sync. The drift detection is a very powerful tool that helps you make sure that your configuration matches the current state of your infrastructure. This concludes our demo on how to use the drift detection tool and how to fix your infrastructure to match your configuration files. Thanks for watching, and see you in the next video. Hello and welcome. In this module, we will explore Resource Manager templates. In OCI Resource Manager, templates provide standardized configurations that simplify and automate the deployment and management of your cloud resources. Templates allow you to define common infrastructure patterns and reuse them across different environments. This enables you to ensure consistency and efficiency in your deployments. By using templates, you can easily manage complex configurations and streamline your infrastructure management processes. Templates can be Oracle-provided or private. Let's see how private templates can be created. In this process, we start with our configuration files, where we define the resources and settings for our infrastructure. Next, we bundle these configurations into a template. This template encapsulates all the configurations and settings from the configuration. The real power of templates lies in their reusability. With a single template, you can create multiple stacks, ensuring consistency and saving time. In our example, we see how a single template can be used to create multiple stacks, stack 1, 2, and 3. This allows for rapid deployment for standardized infrastructure across different environments. Now, let's jump in the console and see how it's done. But before we go to the templates, let me show you a feature that can make your stacks and templates look much more professional and easy to read. Let's go to the navigation menu, Developer Services, Stacks. There's a feature called schema.yaml that allows you to define the dialogues that will be shown to the user that it's creating the stack. Let's create a stack here. Let me find the folder. I have a folder with the schema already. I will import it into. And the difference happens on the next screen for the variables. As you can see here, you have dialogues that show different labels for the variables. If you don't have that, this is how it will look like. So you can see side by side. I added here required configuration. Instead of the OCID of the compartment, I have the name of the compartment, and all of that is done through the schema.yaml that you can drop on the folder. If you take a look at the documentation, you can find a template file that will guide you on how to fill those to fill that file according to your needs. Let's go back here and let's go now see how to create a template. So Developer Services, Private Templates, create a private template. I will go to the folder that holds my configuration. Template with schema, it's the folder that I'm looking for. I will upload the files, my template. Let me fix the name here. Description. Template for 2 VCNs. And with create, that it's done. If you go on the template details, you can go and create a stack, or if you go on the stacks dialog, you can click on create stack, template, select template. You will have the Oracle provided ones first, quick start, service, architecture based. And if you move to the private tab, you will see my template here. By clicking on the box, I can click select template, and it will give you my working directory, the name of my template. I'm gonna call this stack 01. I will click on next. I will fill the parameters here. 10.0.0.0/16. First VCN, I'm going to call it VCN 01. Side block for my second VCN, 10.1.0.016 vcn02. Next. Create, and my stack is ready to deploy. I can come back here, stack, create a new stack, template, select template again, private, and the same options will be displayed over and over each time the template is called to be used. I can change here the compartment to deploy on another compartment, but I can go here and I fill the parameters here. By creating private templates, you streamline your infrastructure provisioning process, make it more efficient, consistent, and scalable. This concludes our lesson and demo on Resource Manager templates. Thanks for watching and see you in the next video. Hello and welcome. In this module, we will explore Resource Manager private endpoints. Let's say you have a Resource Manager stack that provisions your VCN, one public subnet, and one private subnet. In the public subnet, it will create an instance with a public IP, and assuming it has the proper security list or network security groups rules, a provisioner called remote exec can connect using SSH and run commands in the provisioned instance. The same is not true for the instance in the private subnet. To allow Resource Manager to connect to the instance, it will require a private endpoint. The private endpoints can be created using the console or as part of the stack. In your configuration, you will need to add the private endpoint resource. It will require that in your configuration a VCN and a subnet are present. Next, you can use this data block that will relate the private instance and the endpoint to be used in the provisioner. Finally, the remote exec provisioner block, where you will put everything together. The host, coming from the data block, the commands you want to run on the private instance, and the other required options. Please refer to the activity guide for the whole stack code that you can use in your environment. Using Resource Manager private endpoints enhances cloud infrastructure management by providing a secure connection to the private resources. This reduces exposure to potential threats and also helps maintain compliance with stringent data privacy and security requirements, ensuring that sensitive data remains protected within a controlled network environment. Overall, private endpoints offer a secure, efficient, and reliable way to manage private cloud resources.
Hello and welcome to this lesson on DevSecOps Introduction. I am Mahindra Mehra and I am a Senior Training Lead and Evangelist with Oracle University. So let's get started. We all are aware of the typical DevOps workflow. The DevOps workflow using the CI/CD involves integrating continuous integration and continuous delivery or deployment processes to ensure rapid and efficient software delivery. With CI/CD, code changes are automatically built, tested, and deployed to production environments, which enables faster delivery cycles and more reliable software releases. But what about application security? Security is essential for modern apps that handle sensitive information such as credit card details and personal data. To protect this information, security teams must conduct comprehensive audits before releasing any production version. In traditional software development approaches, security practices were often not integrated into the development life cycle, and security audits were typically carried out towards the end of the development process. This approach could result in security vulnerabilities being missed or introduced during the development process, making it difficult to address them later on. Let's explore a few potential scenarios that could result in a security breach. These include using outdated or vulnerable third-party libraries or dependencies. Now, many applications rely on third-party libraries or dependencies to function properly. However, if these libraries are outdated or contain known vulnerabilities, they could be exploited by attackers to gain access to sensitive information or execute malicious code. Leakage of sensitive data. Sensitive data can accidentally leak due to various reasons such as misconfigured access controls, unencrypted data transmission, and human error. Once data is leaked, it can be used for malicious purpose by attackers. Organizations need to implement proper data security policies and controls to prevent such accidental data leakage. Next is vulnerability within container images. We all know containerization is a popular method for deploying and managing applications. However, if container images are not properly secured, attackers can exploit vulnerabilities within them to gain unauthorized access. Regular security assessments and vulnerability scanning can help detect and remediate such vulnerabilities. Lastly, misconfigurations in container orchestration tools. Container orchestration tools like Kubernetes are used to manage and scale containerized applications. However, misconfiguration in these tools can create security vulnerabilities that can be exploited by attackers. It is important to follow security best practices and regularly audit the configuration of these tools to prevent security breaches. However, these issues can sometimes go unnoticed by developers, and as a result, security teams must conduct thorough scans and analyze any changes made to the code in order to identify potential security issues within the application. This process can be time-consuming, taking hours, days, or even weeks depending on the complexity of the application. Once the bug has been identified, they must be passed along to the developer to apply fixes in subsequent versions. However, in the meantime, due to the efficient DevOps workflow, there may be multiple new versions of the applications waiting in the queue for security audits. This can lead to a bottleneck that prevents app releases from entering the production environment for weeks. So why does security audits take so long? Historically, security has often been treated as a lower priority in software development, with more emphasis placed on speed and functionality. Traditional compliance monitoring and security tools were not designed to keep up with the rapid pace of change in a DevOps environment. As a result, they may not be able to detect vulnerabilities or other security issues that arise from the use of microservices, containers, or cloud-based infrastructure, which are often used in DevOps workflow. This can lead to security vulnerabilities going undetected, requiring more time and effort to identify and address, which can slow down the release process. DevOps teams sometimes see security as an obstacle to development speed and efficiency, leading to less attention being paid to security considerations. This can result in undetected security issues that require more time and effort to fix, slowing down the release process. Application delivery involves multiple teams, including the development, security, and operations. However, the misalignment of goals between the developer and security teams often leads to issues in the delivery process. Developers wanted to make new things quickly and in a creative ways, but security teams cared more about making sure everything was secure and met the rules. This is where DevSecOps come in as a solution to bridge the gap and ensure a collaborative and secure delivery process. DevSecOps is the logical conclusion to DevOps' missing component, security. Simply put, DevSecOps is a DevOps extension that codifies security as part of the larger goal structure. To accomplish this, DevSecOps frames security as a shared responsibility where all the teams are working together to find and fix security issues early in the software development process. By collaborating, they can create applications that are safer and of higher quality, all while keeping things moving quickly and efficiently. The idea is to keep development and testing going smoothly without getting held up by security concerns, so that in the end, the application delivered is secure, reliable, and functional. Delaying the considerations of security concerns in the software development process can lead to an increase in the cost and time required to identify and address security vulnerabilities. However, by implementing a shift-left security approach, where security is given greater emphasis earlier in the development process, it is possible to reduce these costs and minimize the time needed to fix security-related issues. The shift-left approach involves incorporating security practices such as code analysis, vulnerability scans, and infrastructure security into earlier stages of development lifecycle, rather than waiting until just before the deployment. To wrap up, we covered the basics of DevSecOps and its benefits, discussed potential scenarios that could result in a security breach, explained why security audits can be time consuming, and explored how shift-left approach can improve organizations' security posture and reduce the risk of security incidents. I hope you found this lesson useful. Thank you for your attention. Hello and welcome to this lesson on applying DevSecOps in OCI. My name is Mahindra Mehra and I am a senior training lead and evangelist with Oracle University. So let's get started. In today's digital landscape, security is more important than ever, and integrating it into your DevOps workflow is crucial for ensuring the safety of your applications and data. In this session, we'll explore the various security options available when working on DevOps projects with the help of this diagram. When a developer commits code to a repository, they must follow certain policies and permissions when using DevOps code repositories. To integrate with third-party code repositories such as GitHub or GitLab, developers need to create a personal access token to obtain permissions to access the code. Now, to ensure the security of these tokens, they are stored in an OCI vault, which provides a safe and reliable method for storing sensitive data. Once the code is committed to a code repository, it can trigger a CI/CD pipeline. When we use a CI/CD tool to build our applications, we have access to some powerful capabilities. For example, we can use a service called Application Dependency Management to help identify security weaknesses in our software applications by checking their dependencies. This service relies on scores provided by the Common Vulnerability Scoring System, which is an open framework used to communicate the severity of software vulnerabilities. In order to use this service, we need to configure it during the managed build stage of our DevOps pipeline. We can also use third-party tools like Sonatype, SonarQube, or OverOps to analyze our code for security defects or bugs in code quality. These tools helps us make sure that our code is as secure and reliable as possible. Once we have built our container image, we can push it to an Oracle Cloud Infrastructure Registry repository with scanning capability enabled. The CI/CD tool then uses the vulnerability scanning REST API to obtain the results of image scan. Now, based on the results of the scan, the CI/CD tool can decide whether to move the image to the next stage in the lifecycle or not. This is an important step in ensuring that our applications are secure and reliable. Once the code analysis and image scanning process have been completed successfully, the CI/CD tool moves on to automated testing. During this stage, we typically conduct security, API integration, and user interface testing to ensure that our applications and code are working as intended. If the tests pass, it's a good idea to add a control stage approval within the deployment pipeline. This involves pausing the deployment for a specified period and notifying an approver of the deployment. The approver will then manually provide approval before the deployment can proceed. This is an important control measure that helps us ensure that our deployments are secure and reliable. Once the deployment pipeline has been approved, the application and code are deployed to the production environment of the OCI platform. The deployment can be done on various OCI platforms such as compute instances. Now, this includes both virtual machines and bare metal instances. To ensure that our deployments to compute instances, Container Engine for Kubernetes, also known as OKE, and OCI functions are secure, we can take several steps. For example, we can use security lists and network security groups to control inbound and outbound traffic to our compute instances. We can also use compartmentalization and identity and access management policies to restrict access to our resources and limit the action that can be taken on them. You can also deploy to a serverless function platform called OCI functions. Similarly, when deploying to OCI functions, we can use identity and access management policies to control access to our functions and protect them from unauthorized access. We can also use encryption and key management to secure our data and protect it from potential attackers. When deploying to OKE, we can use Kubernetes security features such as role-based access control and network policies to ensure that only authorized users and services can access our applications and services. We can also use secrets management to securely store and manage sensitive information such as passwords, API keys, and other credentials. Continuous monitoring of our application's environment is essential for identifying security issues. We can use OCI's monitoring tools such as APM, monitoring, and logging. Configure them to use OCI's native functions like notification for quick response to security threats. We can also integrate logs with ServiceNow or third-party SIEM systems to streamline security issue resolution. To wrap up, we've learned about implementing DevSecOps in OCI DevOps project and utilizing its security services to secure your DevOps environment. I hope you found this lesson useful. See you in the next one. Thanks for watching. Hello and welcome to this lesson on DevSecOps best practices. I am Mahendra Mehra and I am a senior training lead and evangelist with Oracle University. How do you ensure the security of your application in a fast-paced DevOps environment? Let's explore the best practices and tools for implementing DevSecOps in Oracle Cloud Infrastructure, so you can confidently deliver secure and reliable software to your customers. Enforcing policy and governance is the foundation of a strong DevSecOps process. It ensures that security is built into the development lifecycle from the very beginning and helps reduce the risk of security breaches. Identity and access management is a critical part of policy and governance in DevSecOps. It involves managing user identities, roles, and permissions to ensure that only authorized personnel have access to sensitive resources. Privileged access management involves controlling and monitoring privileged access to critical systems and data to prevent unauthorized access or misuse. To enforce policy and governance in DevSecOps, it is important to define roles and responsibilities for everyone involved in the development process, from developers to operations teams to security personnel. Training and education are crucial for effective implementation of security controls in DevSecOps. Staying updated with the latest safety techniques and best practices is equally essential to keep pace with the evolving threat landscapes. Automating DevOps security processes and tools is essential to reduce the risk of human errors and security incidents. By leveraging efficient tools and automation, organizations can streamline their DevOps security processes, resulting in faster and more resilient applications. Oracle Cloud Infrastructure provides a range of security tools for DevOps teams to use, including code analysis, configuration management, patching, and vulnerability management tools like OS management and Oracle Vulnerability Scanning Service. Additionally, privileged credentials and secrets management is offered through OCI's Vault service. To ensure the security of your OCI assets, it is crucial to perform comprehensive discovery of all devices, tools, and accounts in your environment. This process helps ensure that all assets are validated and monitored continuously in accordance with your security policy. By doing so, you can align your assets to adopt a zero trust security model, where no user or device is trusted by default. This approach can help mitigate the risk of potential security breaches and ensure that your security policies are consistently enforced across all assets. You must make sure to regularly scan for vulnerabilities in your applications and systems and prioritize fixing them based on their severity. It is also important to follow established security guidelines, such as the OWASP DevSecOps guideline during the development and testing process. This helps ensure that security is built into the application from the start and reduces the risk of security incidents in production. In a DevOps environment, managing credentials and identity accounts in code is critical to ensure secure access. Utilizing a secrets management tool like Vault can help prioritize security and effectively manage the lifecycle of secrets. In order to ensure secure access to your infrastructure, it is important to implement privileged access management policies. With the help of Oracle Cloud Infrastructure services such as IAM, DevOps IAM policies, logging, and monitoring, you can effectively control, monitor, and audit access to your resources. This helps to prevent unauthorized access and protect against security threats. When implementing DevOps processes, it is important to segment networks to reduce the attack surface and isolate different work environments, such as production and development or test environments. This helps ensure that security risks in one environment do not impact others and provides better control over access and security policies. To wrap up, we've discussed best practices for securing your applications in a fast-paced DevOps environment. By staying up to date on the latest safety techniques, providing proper training and education, and leveraging OCI's security tools, you can confidently deliver secure and reliable software to your customers. I hope you found this lesson useful. See you in the next one. Thanks for watching.
Hello and welcome to this introductory lesson on the OCI Vault service. In this lesson, we'll explore some fundamental concepts and capabilities of OCI Vault. I am Mahindra Mehra, your senior OCI instructor with Oracle University. So let's get started. OCI Vault is a service managed by Oracle that allows you to centrally manage your encryption keys and secret credentials. It supports 3 encryption algorithms: AES, RSA, and ECDSA. Besides providing encryption for password credentials to be used with any external application, the Vault service integrates with OCI SDK, CLI, or API clients and also integrates directly with several OCI services behind the scenes. The primary components include vaults, keys, and secrets. I will cover each of these elements as we proceed in this course. Essentially, the Vault service eliminates the need to store encryption keys and secrets in configuration files or code. As a best practice, DevOps engineers should use Vault to enhance the overall security posture of their application and service deployments. To use the Vault service, you begin by creating one or more vaults. Each vault acts as a logical container that allows you to create and durably store your keys and secrets using the service. When creating a vault, you choose between two types. The first type is a virtual private vault, which is essentially a dedicated, isolated partition in a hardware security module, also abbreviated as HSM. With this option, you can store up to 1000 key versions and benefit from better isolation since it's dedicated to you. Another advantage is the ability to back up the vault and the keys you have created to an OCI object storage bucket, which supports disaster recovery scenarios and cross-region replication requirements. This option is considered the more advanced version of the product and comes with a higher cost. The default option is to provision your vault in a shared partition. While this option is still completely secure, you share the HSM partition with other Oracle customers. As a result, you don't get some of the advanced features such as the ability to back up to object storage. However, it's more cost effective because you're only charged for the actual number of keys, key versions and secrets stored. So now, what are keys? Keys are logical entities that represent one or more versions of cryptographic material. These keys are generated for a specific algorithm. You can create and use AES symmetric keys or RSA asymmetric keys for encryption and decryption. Additionally, RSA or ECDSA asymmetric keys can be used for signing digital messages. In the Vault service, there are three conceptual types of keys: master encryption keys, data encryption keys, and wrapping keys. Let's take a closer look at each of these. To better understand, master encryption keys are the keys that you create or import into your vault. You select the encryption algorithm and key shape, such as the number of bits for AES and RSA or the elliptic curve ID for EDCSA. You also select the protection mode from the list of options, which I'll be discussing further. Additionally, there is the concept of data encryption keys, which are generated by master encryption key. Data encryption keys themselves are dynamically encrypted with a master encryption key, a process known as envelope encryption. OCI services such as block or file storage either use Oracle managed keys, or you can specify a custom master key from your vault for specific use cases such as one or more object storage buckets or a specific block volume. As noted earlier, when you create a new master encryption key, you decide on one of the two protection modes. The first option is HSM, where your key is backed by a highly available and durable hardware security module, and all cryptographic operations take place inside the HSM. However, with this option, the key cannot be exported to an external client. This is the most secure option, but it is also more restrictive. The second option is software, where the master encryption key is stored on an internal server. In this case, it can be exported to perform cryptographic operations on a client instead of just the server. However, these keys are fully protected while at rest, since they are encrypted by a root key on the vault's HSM partition. It's important to note that there are different pricing models depending on which protection mode you choose to use. The third type of key used by the vault service is a wrapping key, which is automatically included with each vault. You use the public portion of the wrapping key pair when you need to import an external key into your vault. Since the vault has access to the private wrapping key, it can unwrap it, so it can be imported as another master encryption key. So instead of letting the vault generate your master keys, you might wish to leverage the bring your own key strategy for various reasons. You may need to use keys that have been generated by some other tool or source based on your requirements. Alternatively, you might wish to use the same keys that you're already using in other cloud environments or in private on-premise systems. Some choose to simply leverage the vault service for the management of their external keys, such as storage, expiration, and deletion. Or perhaps you wish to own and handle your keys outside of OCI for additional durability and recovery use cases. Finally, let's discuss rotating these master keys. As mentioned earlier, each key is automatically assigned a key version when you create the key for the first time. When you rotate a key, a new version is automatically generated, or you can choose to import another key. It's considered a best practice to periodically rotate a master encryption key. This practice limits the amount of data that is encrypted or signed by just one version of the key, which can significantly reduce the risk of data integrity if a key is ever compromised. Now, you might be wondering, if we rotate the key, how does the vault service handle decryption? For example, if encryption was done with version 1, but now we are using version 2, well, behind the scenes, the vault leverages the unique Oracle Cloud identifier of the older key version as needed. While older versions can't be used for encryption anymore, they will still be used to decrypt data that was encrypted earlier with a previous version. In summary, the OCI Vault service offers secure management of encryption keys and secrets with features such as key rotation and versioning. I hope you found this lesson useful. See you in the next lesson. Thank you for watching. Welcome back. In this lesson, we'll explore how your Vault can be seamlessly integrated with a variety of other OCI services. I am Mahendra Mehra, your senior OCI instructor with Oracle University. So let's get started. In our Vault introduction lesson, we mentioned that several OCI services can integrate directly with a Vault for managing data encryption. Here's the current list: object storage buckets, file storage, boot and block volumes, streams within a stream pool, Kubernetes secrets in an OKE cluster, and autonomous container databases. This list will continue to grow, so be sure to check our online documentation for the latest updates. It's important to note that the scope for all these services is regional, meaning you will be designating master keys from vaults located in the same region as the OCI service. Before we dive into integrating the Vault service, let's review how Oracle Cloud manages data encryption for OCI services. By default, Oracle handles data encryption and decryption using an Oracle managed master encryption key, provided you've selected that option as shown here, when provisioning resources like a block volume, object storage bucket, or an OKE cluster. Therefore, even if you are not using the Vault service, data stored in these OCI services, commonly referred to as data at rest, is always encrypted. This encryption cannot be turned off, which is a crucial point to remember. With Oracle managed keys, a master encryption key from an internal Oracle managed vault generates a data encryption key for the respective services to encrypt data. When you opt not to use Oracle managed keys, you can leverage the OCI Vault service by selecting a master encryption key from your own vault. As shown on the screen, you locate your vault and choose the key you wish to use. There are various security reasons for doing this, but the most common use case is when provisioning resources in a designated security zone compartment. In such cases, buckets cannot use an Oracle managed encryption key and must use a master encryption key from your own vault. Remember, the customer managed keys option shown here is different from the bring your own key option mentioned in the introduction lesson. Customer managed keys are simply keys maintained within your vault. This could be a key you imported in your vault or one generated by the Vault service when you created it. Either way, the key belongs to you and you manage its life cycle, including rotating key versions. So now let's take a visual look at how all of this works under the covers, as it's an important concept to understand. Here is your vault backed by a hardware security module which is FIPS 140-2 Level 3 compliant. Within OCI Vault Service, leveraging the Identity and Access Management Service, you define authorization policies to determine which services and users have access to your vault, even down to a particular key. In this example, someone is adding plain text data such as a log file into an object storage bucket. Before it can be stored, it needs to be encrypted. Let's see how this process works. The object storage service requests a data encryption key along with a copy of the key encrypted with a master encryption key from the vault service. Upon receiving the keys, the object storage service uses the plain data key to encrypt the log file data and then immediately removes that key from memory once it's used. Now, the encrypted log data file and the encrypted data key are stored in the bucket. Even if someone gains access to these artifacts later, they cannot decipher the data because the data key itself is encrypted, keeping the data fully protected. Only a system or entity with access to your vault can request a decrypted plain data key to decrypt the data file. Now let's reverse the process. Since the encrypted data key is stored in the bucket, when the object storage service needs to decrypt the data, it first sends the encrypted data key back to the vault to retrieve a plain data key. The vault service uses the appropriate master encryption key to remove the envelope encryption and sends the decrypted data key back. The object storage service can now use the key to decrypt the file, the ciphertext, back to plain text, which is our log file. Once again, the service immediately removes the plain data key from memory once the process is complete. So this is how the process works end to end. Keep in mind, the object storage service or any other service integrated with Vault has no access to plain data key until it is retrieved each time from the vault. Therefore, your data at rest is always protected. Although we used object storage for this example, a similar process is followed for all other integrated OCI services such as block volumes, OKE clusters, and the file storage service. To wrap up this lesson, we covered how the Vault service integrates with various OCI services. We explored how encryption and decryption process works, the role of Oracle and customer managed keys, and the security benefits of using OCI Vault. I hope you found this lesson useful. See you in the next one. Thanks for watching. Hello and welcome to this lesson on OCI Vault Secrets. Let's explore the fascinating world of securing sensitive information within OCI. I am Mahindra Mehra, your senior OCI instructor with Oracle University. So let's get started. As you may recall from my introduction to OCI Vault lesson, we discussed the key element of the Vault service, including the Vault itself backed by a FIPS 140-2 Level 3 hardware security module, which can be either a shared or private HSM. Additionally, we touched upon the creation or importation of master encryption keys into your vault. However, up till now, we haven't covered the third crucial element, which is secrets. Secrets encompass credentials such as passwords or tokens, along with any other confidential data necessary for use with other Oracle Cloud Infrastructure services or external applications or systems. Storing secrets in a vault offers significantly greater security compared to storing them elsewhere, such as in code or configuration files. Furthermore, you can retrieve secrets from the vault service as needed to access resources or other services. Secrets can be created via the OCI console user interface as demonstrated here, or programmatically in code or scripts using the OCI SDK, CLI, or REST API. Each secret is automatically assigned a version. When you rotate a secret, you provide new secret contents to the Vault service to generate a new version. Periodic rotation of secrets reduces the impact in case a secret is exposed. The secret is also assigned a unique Oracle assigned identifier, also known as OCID. This ID remains consistent across rotations, enabling the Vault service to rotate secret contents to comply with any rules or compliance requirements you may have, while maintaining consistent programmatic access. Optionally, you can apply rules to specific secrets to enhance security further. The first rule involves preventing the reuse of secret contents, thereby limiting the scope of affected resources in the event of a security breach. Additionally, you can deprecate and then delete a secret version if it can no longer be safely used. You also have the flexibility to choose whether secret reuse rules apply even to the deleted secret versions. Another important feature is the ability to configure an expiry rule to specify a time interval for how long a secret version can exist. The longer credentials are used, the greater the opportunity for attackers to access or decipher them. Therefore, it's advisable to frequently update secrets with new contents to mitigate risk associated with compromised credentials. You can configure a secret version to expire anywhere from 1 to 90 days. Alternatively, you can set an absolute expiration date and time for the secret ranging from 1 day to 1 year after its creation date. You have the flexibility to configure either or both of these values, and you can decide whether the secret contents are blocked past the expiration date. To better understand how to use secrets, let's first take a quick look at the OCI console user interface and create a secret. I've already logged into my OCI console and this is my OCI dashboard. I'll start by accessing the OCI Vault service, for which I'll click on the navigation menu, go to Identity and Security, and within the Key Management and Secret Management section, I'll click on the Vault offering. On the Vaults page, as you can see, the compartment selected is Mahindra, and I already have a vault created with the name Mahindra_vault. I'll click on the vault name. Within this vault, I have a few master encryption keys available, and these keys can be software or HSM based, and they support various algorithms like AES, RSA, or ECDSA. Now let's focus on the secrets. I'll click on the secrets link from the resources tab, and I have pre-created a secret called ADB username. To save some time, let's check its details. I'll click on the secret name. Currently, there's just one version of this secret. If I want to view its content, I can click on this action menu and click on View Secret Contents. By default, it shows the base 64 value, but I can switch to see the clear text which says Mahindra. So here you can see that the ADB username value is Mahindra. I'll click on Close. Now for this demo, I'll create a new secret for the database user's password. I'll go back to the Vault and click on Secrets. Under Secrets page, I'll click on Create Secret. This opens up the Create Secret window, and you must ensure that you have chosen the right compartment where you wish to create the secret. Provide a name for the secret. In my case, it's ADB-password. Let's give it a description which will be helpful for anyone reviewing it later. Next, we must select the encryption key. I'll choose the one that already exists in my vault, which is Mahindra_MEK. And now, since I want to pass the ADB password value manually, I'll choose the manual secret generation option. And here you can specify the secret contents either in plain text or using base 64 value. I'll go ahead with the plain text option. and let's provide a demo password. Now after specifying the secret contents, I can also see its base 64 conversion by enabling show base 64 conversion option. Under the secret rotation field, you can specify the target system type and its ID, or you can also enable the auto rotation for your secret by just checking this box over here and specify the rotation interval in months, which is 1, 3, 6 or 12 months. For now, I'll disable this. I'll go ahead and click on create secret. Well, as you can notice, in no time my secret ADB password has been created and the status says active. Now let's understand what is required to use these secrets programmatically or in a script. I'll click on one of the secrets, which is ADB username, and each secret, as I mentioned in our lesson, contains an OCID. OCID is the Oracle Cloud Identifier. As you can notice, this is the OCID for the ADB username secret. You can copy the OCID or you can click on show to view the OCID value, and this is what it looks like. Now this OCID is essential for developers as it remains the same no matter how many times we rotate or update the secret's content. So for example, the OCID associated with the ADB username will always be the same, providing consistency. Similarly, the password we just created will have its own unique OCID. Let me go to the password secret. And here is the OCID for the ADB password secret that we created. So these secrets that we create, they have their own unique OCID, which we'll be using in our environment. Now let's continue with our lesson. As a reminder, for automating security requirements, the DevOps engineers can manage all these configurations programmatically using the Vault CLI or API in scripts or code instead of manually in the OCI console. This includes obtaining a secrets Oracle Cloud ID, also known as OCID. And now that we have the OCID of each secret, in this Kubernetes example, I have introduced two new Vault variables in the YAML build file. These variables are utilized to build the code, create a container image, and subsequently deploy it to an OKE cluster. The maven build command will reference these variables, specifically the database username and password in this instance. In this Oracle Functions example, instead of defining hard-coded variables used to connect to the OCI container registry within this YAML configuration file, I replace them with Vault variables which are set to the Oracle Cloud IDs of those two secrets in my Vault, which is the username and password. And for any other use case that doesn't necessarily involve microservices deployed within an OKE cluster or Oracle Functions, you can still dynamically retrieve the secret credentials using OCI Vault API or CLI programmatically, using the same secret OCID. For more detailed information on leveraging the Vault CLI, API or SDK functions, be sure to review our online documentation and tutorials. To wrap up this lesson, we delved into the management and utilization of Vault secrets, exploring their critical role in enhancing security within OCI. I hope you found this lesson interesting. See you in the next one. Thank you for watching.
Hello and welcome to this lesson on Application Dependency Management Overview. I am Mahendra Mehra and I am a Senior Training Lead and Evangelist with Oracle University. So we all know Trisha, right? This time around, Trisha was worried about the security and compliance of their pharmacy applications' CI/CD workflows. She asked Mo if OCI DevOps provides a method for ensuring best practices in this regard. Mo responded positively but wanted more information about Trisha's specific requirements. Trisha then explained how a recent code release into the production had a security bug that went unnoticed. And although they fixed it eventually, The process of scanning and patching the vulnerability was a manual one. Mo was concerned about the potential consequences of such a security breach. Trisha realized that they need to find a way to automate security compliance in their DevOps service pipelines. They discussed several options, and finally, Mo suggested utilizing the OCI application dependency management service. Now, before we get into the specifics of what the OCI application dependency management service does, for a better understanding, let's go over a few key concepts and terminology. Vulnerability is a weakness that can be exploited by attackers to gain unauthorized access to a computer system. For example, dependency vulnerabilities. If the dependencies used in the application development are not updated regularly, they can contain known vulnerabilities that can be exploited by attackers. Next is common vulnerabilities and exposures, also known as CVE. Common vulnerabilities and exposure is a dictionary of publicly disclosed computer security vulnerabilities and exposures. Each CVE contains a unique identifier, a description of the vulnerability or exposure, and information about any known software or hardware that is affected by the vulnerability. This information can be used to track and reference the vulnerability in various databases, tools, and reports. CVE is maintained by the MITRE Corporation, a non-profit organization that operates federally funded research and development centers. Other organizations, such as the National Vulnerability Database, also abbreviated as NVD, use CVE identifiers to categorize and index vulnerabilities. CVSS stands for Common Vulnerability Scoring System. It is a framework for assessing the severity of computer systems vulnerabilities based on various factors such as the potential impact of the vulnerability, how easily it can be exploited, and the level of access required to exploit it. The CVSS framework assigns a numerical score to each vulnerability ranging from 0 to 10, with higher scores indicating greater severity. Scores from 0.1 to 3.9 indicate a low level of severity. Scores from 4.0 to 6.9 indicates a medium level of severity. Scores from 7.0 to 8.9 indicate a high level of severity. And scores from 9.0 to 10.0 indicate a critical level of severity. When a new vulnerability is published in the National Vulnerability Database, it will have a CVSS score assigned to it using either the CVSS version 2 or CVSS version 3.x scoring systems. Let's understand vulnerability audits. A vulnerability audit describes the vulnerabilities of your application and its dependencies. A vulnerability audit in the OCI is associated with a knowledge base. Talking about knowledge base, a knowledge base is associated with vulnerability audits, and when you configure a vulnerability audit, you specify the knowledge base with which it is associated. Knowledge base is required to contain the results of Application Dependency Management Service. Now let's cover the Application Dependency Management Service in detail. The Application Dependency Management Service in Oracle Cloud Infrastructure helps detect security vulnerabilities in the dependencies of your application. This means that the ADM scans all the external libraries and frameworks that your application relies on and alerts you if there are any known vulnerabilities. ADM relies on scores provided by the Common Vulnerability Scoring System, which is an industry standard scoring system that assigns a severity score to security vulnerabilities. The CVSS score helps you understand the potential impact of a vulnerability and prioritize which vulnerabilities to remediate first. ADM is a tool that can benefit many different teams within your organization, whether you are a developer, operations specialist, DevOps engineer, or support team member. ADM can help you answer critical questions about your application dependencies by identifying which dependencies your application relies on and which ones contain security vulnerabilities. ADM is typically configured in the managed build stage of a DevOps pipeline. This means that the ADM will automatically scan your application for vulnerabilities as part of the build process, allowing you to identify and remediate any issues early in the development cycle. By integrating ADM into your DevOps pipeline, you can ensure that your applications are secure and reliable from the very beginning. Once ADM has identified vulnerabilities in your application dependencies, it is important to take action to remediate them. One way to do this is by updating your dependencies to the most current secure versions. By keeping your dependencies up to date, you can ensure that your application is running on the most secure and reliable code possible, which reduces the risk of security breaches and any other issues. To wrap up, we covered some important terminology and concepts and understood how OCI Application Dependency Management Service can be leveraged to gain valuable insights into your application dependencies and proactively address potential security vulnerabilities, helping to ensure that your applications are secure, reliable, and perform at their best. I hope you enjoyed the lesson. See you in the next one. Thanks for watching. Hello and welcome. In this lesson, we will explore ADM-IAM policies and provide a detailed walkthrough of the steps necessary to set up ADM service and vulnerability audit in the OCI DevOps build pipeline. Let's take a look at the application dependency management IAM policies. The following slide lists the permissions covered by each of the individual resource types included in the ADM family. The level of access is cumulative as you go from inspect to read to use, and use to manage. As you can see on the screen, individual resource types include ADM knowledge base, ADM vulnerability audit, and ADM work request. You can also go for aggregate resource type, which includes all of these individual resource types, which is labeled as ADM family. Currently, you can see the permissions available under the ADM knowledge base individual resource type. So the different level of access and permission that one can have with the ADM knowledge base are inspect, read, update, create, delete, and move. Also make a note that all permissions has prefix ADM underscore knowledge underscore base underscore the permission name. The list of permissions for ADM vulnerability audit resource type doesn't really change. The only thing that you have to note is the permissions has prefix ADM underscore vulnerability underscore audit underscore the name of the permission. And when we talk about ADM work request, here we have limited permissions, which includes inspect, read, update, and cancel. And again, all the permissions has prefix ADM underscore work underscore request underscore the permission name. Let's look at some of the sample IAM policy syntax for the ADM service. So this set of service lets a user group work with the ADM service. As you can see, we are allowing the user group ADM admins to manage ADM knowledge bases, ADM vulnerability audits, and ADM work requests in a certain compartment. Here we have specified all the individual resource types. You can also choose to use the aggregate resource types to write fewer policies. So you can replace the above 3 lines with a single line of managing ADM family in a compartment. You can also assign the IAM policies to a certain user group based on the where clause. This limits the level of access provided to a certain group of users. Let's break down the steps necessary to get ADM set up with the OCI DevOps service. So as part of step 1, you have to ensure that you have set up the required ADM IAM policies as we discussed in the previous slide. In step 2, you need to ensure that you create a knowledge base within the ADM service. Knowledge base is required to contain the results of ADM. Here are the screenshots of how to create knowledge base. So you must go to the ADM service in the OCI console and click on create knowledge base, give it a suitable name, and click on create knowledge base again. Step 3 is creating a DevOps project and build pipeline. Oracle Cloud Infrastructure DevOps build pipeline service now includes a new security vulnerability scanning capability for application builds. Step 4 requires you to add the vulnerability audit build step. Vulnerability audit step can be added to existing DevOps service build instructions in the build underscore spec file. Let's talk about adding vulnerability audit build step in more detail. So as you can see, with this simple configuration, developers can control the configuration of the scan to pass or fail. Let's try to understand this configuration in more detail. Vulnerability audit step can be added to the existing DevOps service build instruction in the build_spec file, where you specify the type as vulnerability audit and give it a name. Under configuration, currently it's supporting Maven dependencies based on pom.xml files. So you need to specify the build type and you need to specify the POM file path. Under packages to ignore, developers can ignore certain artifacts or versions path. For example, you can specify that you have tolerance for certain medium or low severity CVEs or for specific packages like struts in the example. You can control the maximum permissible CVSS scores that is allowed within the project. I've already discussed the severity scores earlier. Lastly, you need to specify the OCID of the knowledge base created in step 2. You also have to specify the OCID of the compartment containing the knowledge base, and you need to provide the name for the vulnerability audit report. This is the name with which the vulnerability audit reports get created within the ADM service. Now let's try to understand how the ADM service works with a diagram. When a developer commits code to a source code management repository, it triggers the manage build stage of the OCI DevOps build pipeline. A build environment is set up and the steps within the build_spec.yaml file are executed. Vulnerability audit step reads the dependencies listed in the pom.xml file for the Maven project. The dependencies are then passed to the vulnerability knowledge base to check for any possible common vulnerabilities and exposures against them. If any CVEs with their corresponding CVSS scores are found, they are checked against the max permissible CVSS score. If the CVSS score is greater than the max permissible CVSS threshold, the build pipeline will fail. And if the CVSS score is below the threshold, the build pipeline executes successfully. And lastly, you need to view the vulnerability audit results. You can view the full tree of application dependencies along with the associated CVEs, examine the CVE scores to comprehend the issue and address the vulnerabilities. This is how the vulnerability audit results looks like. It contains the application dependencies, their equivalent CVEs and CVSS scores. To wrap up, in this session, we covered ADM IAM policies and steps necessary to configure vulnerability audit for application dependencies using OCI ADM and DevOps service. I hope you enjoyed this lesson. See you in the next one. Thanks for watching. Hello and welcome to this demo on scan for common vulnerabilities and exposures in Maven builds as part of your OCI DevOps build pipeline execution. So let's get started. Alright, so I've signed in to my Oracle Cloud account and this is my OCI console. In this demo, we will be seeing how the new vulnerability audit feature enables you to scan for common vulnerabilities and exposures as part of your continuous integration pipelines. Currently, the support is for Maven dependencies based on pom.xml files. We will be adding a vulnerability audit step for the sample Maven project within the DevOps service build instructions, and those instructions are specified in the build_spec.yaml file. So this is the repository that I'll be using for the demonstration purpose. As you can see, I have a pom.xml file which contains all the dependencies required to build my Maven project. These are all the dependencies that I've listed out here. And as you can see, there's one dependency that I've listed called log4j. And if you're not aware, the versions of Apache log4j prior to version 2.15.0 have been found to contain a serious security vulnerability that could potentially allow remote attackers to execute arbitrary code on a target system. For the demonstration purpose, I've used a vulnerable version, and we'll be seeing how the vulnerability audit step detects this dependency and its version and flags it as a security vulnerability. Now if you check the build_spec.yaml file, as you can see, we have defined a vulnerability audit step. What this audit step does is it checks for the pom.xml file. Since the support is currently for Maven based projects, it reads all the dependencies mentioned in the pom.xml file and compares those dependencies versions with the knowledge base. It checks for the CVEs associated to those versions of the dependencies mentioned. You can also specify the packages within your dependencies that you wish to ignore. You must set the max permissible CVSS score. We have set the CVSS score for both the versions, version 2 and version 3. How this works is, if a CVSS score for a CVE that was detected against a particular version of dependency mentioned in the pom.xml file is, if it's greater than the mentioned threshold, then the build pipeline will fail. This will alert the developer about the security vulnerability. And if the CVSS for the CVE detected is less than the maximum permissible CVSS score, then the build pipeline will go green. And then you must specify the knowledge base OCID over here. You must also specify the OCID for the compartment where the vulnerability audit reports will be generated. It's basically the compartment in which you've created the knowledge base. And you must give your report, vulnerability audit report, a name. Alright, so let me go back to the OCI console. And in the interest of time, I have already pre-created a few resources. For example, I've already created a DevOps project. This is the DevOps project, which is mirroring my GitHub code repo. So if I click on Code Repositories, as you can see, this is the mirrored code repo of my GitHub repository. These two files are present over here as well. So now let me go ahead and create the knowledge base in the ADM service. So to do that, let's click on the hamburger icon, go to the developer service, click on knowledge bases under app dependency management. Let's go ahead and create a knowledge base. Click on create knowledge base. Make sure you are in the right compartment. Let's click on create knowledge base. Give it a suitable name. Make sure you're creating the knowledge base in the right compartment. Click on create knowledge base. Now once the knowledge base is created, you must copy its OCID and paste it in the vulnerability audit step. Alright, so my knowledge base is active. I'll simply copy the OCID, go to my GitHub repo and edit this file. Paste the knowledge base OCID over here. Make sure that you provide the compartment OCID where you created the knowledge base. This is the OCID of the compartment where I created the knowledge base. And you can give a suitable name to the vulnerability audit report that generates when the build runs. Alright, so let me go ahead and commit this change. Okay, so now let's go back to the DevOps project and create a build pipeline. So to go back to the DevOps project, click on developer service, click on DevOps projects. Let me click on the DevOps project that I had pre-created. Click on build pipelines. Click on create build pipeline. Give it a suitable name. And click on create. Alright, so let's go ahead and add a manage build stage in the build pipeline. Click on next. Give the stage a suitable name. I'll leave everything as default. Make sure you select the primary code repository. So let me click on select. Let me select the connection type as OCI code repository. This is the mirrored code repository, right? So I'll select this. The branch is main and the build source name is github_adm-demo. So let's go ahead and click select. And now let me go ahead and click add. Alright, so the manage build stage has been added in the DevOps build pipeline. Alright, so let's go ahead and start the manual run. Let me click on start manual run over here. Now as you can see, the build run is in progress. Initially, it will set up the build environment. Alright, so as you can see, the vulnerability audit step has failed, which means the build pipeline has failed its execution. So in order to check why the build pipeline failed, we can go to the ADM service and check if there is a vulnerability audit report that's been generated. So let's go to the ADM service and check for vulnerability audit reports. Click on the hamburger menu, go to developer service, click on vulnerability audits under app dependency management. And if you notice, there is a vulnerability scan report that's been created. Ignore the previous ones, those are part of my test run. So this is the current vulnerability scan report that's generated. So if I click on it, you'll notice that the max observed score is 9.8 for the dependencies that we had listed in our pom.xml file. So as you can see, the log4j dependency which we had mentioned in the pom.xml file, for the version 1.2.16, there are CVEs which are listed, and there are CVSS scores which stands in high and critical severity. Since the max permissible CVSS score specified by us was 6.0 and the detected one is 9.8, the build run failed. So if I take you to the build_spec.yaml file, the max permissible CVSS score set by us was 6.0. And this is the reason why the build failed. So based on this assessment, let's go back to the pom.xml file and change the version from an older version to the most latest one and rerun the build pipeline. So to do that, let me go to my repository, go to the pom.xml file, and let me quickly edit this file and change the version from 1.2.16 to the latest one, which is 2.17.1. Let me go ahead and commit this change. Alright, so I've committed this change. Now my log4j dependency has the version 2.17.1. So let's go back to the OCI console and go to the DevOps service. And make sure that the change made in the pom.xml file reflects in the code repository over here. Since it's a mirrored repository, the changes will be synchronized. As you can see, the mirroring is in progress. Once this is done, we will be able to see the updated version in the pom.xml file. Let's check if the version is updated. Alright, so as you can see, the new version has been updated in the code, which is 2.17.1. Now this version of log4j is free of vulnerabilities. So let's go back to our DevOps project and run the build pipeline. Let me click on the DevOps project. Go to the build pipeline. Click on the build pipeline. And if you see the build history, the previous build run had failed, right? Because it had detected a vulnerability in the log4j previous version. But now since we have updated the log4j dependencies version to the latest one, let's see if it detects any vulnerability or it passes the build. Let's go to the build pipeline, click on start manual run. Click on start manual run. Alright, so the manual run has successfully started. So let's wait for the build run results. In the meanwhile, let me duplicate this tab and open the ADM service. Let's open the application dependency management service. Let's go back to the build pipeline and wait till it executes. Alright, so as you can see, this time around the vulnerability audit step has passed and the build pipeline has succeeded. Right, so if you check the build history, the previous one failed and the current one that ran has successfully completed. Right, so let's go to the knowledge bases and click on vulnerability audits. You will see a new vulnerability scan report is generated, which states that the number of vulnerable artifacts is 0 and the maximum observed score is again 0, which means it could not find any CVE against the latest version of log4j. Right, so let me click on the scan report. If you see, under the application dependencies, there are no dependencies that have any sort of vulnerabilities or CVSS score assigned to it. So with this, we come to the end of this demo. I hope you enjoyed the demo. See you in the next one. Thanks for watching.
Hello and welcome to this module, an introduction to observability platform with Oracle Cloud Infrastructure. My name is Tijo Thomas and I am a cloud evangelist at Oracle University. In this lesson, we are going to look at the key services and capabilities of the observability platform and how it addresses the priorities University. In this lesson, we are going to look at the key services and capabilities of the observability platform and how it addresses the priorities of DevOps. We will start with looking into the top priorities that could be addressed with observability. Number one, information systems end-to-end protection, which means maintaining the end-to-end security of all information systems, whether it could be the physical data center, networks, or applications. Number two, understanding the internal workflow of systems. DevOps would require a complete understanding of the internal workings of their systems, and that would help them to choose the right metrics to monitor proactively. Maximize agility in application delivery. The ability to quickly deliver applications with having continuous monitoring to identify issues in the early stages. For example, finding performance issues with applications, and we refer to this concept as the shift left monitoring. This process would monitor constantly for health checks and find performance issues early during the process. Accelerate MTTD or mean time to detection and MTTR or mean time to resolution. This is one of the top priority in how quickly to detect issues or the mean time to detect and how quickly to resolve them or mean time to resolve. Reduced cost for breaches and operations. DevOps would also need to introduce processes or workflows that would reduce the overall cost of any breaches and including operational efficiencies benefiting to that cost savings. With proactive monitoring and quick resolution, the overall cost can be reduced. Improve services and customer satisfaction. DevOps engineer would also look to improve cloud services with leveraging the datasets and metrics and consuming them with best practices, which can all add values to the customer. Let's now look into the end-to-end workflow of DevOps and define observability in this architecture. DevOps practitioners are continuously making changes to their code, and it gets checked in or committed into the code repository. The code repo is a platform where you host the entire code, including any software archives. So it is really important to monitor these code repos, or let's say if you want to monitor the total size of this repository. The next stage is the build pipeline, and it is the stage where this code gets compiled and makes it ready for deployment. The build pipeline would also